should get started. Hello everyone, I am Ayush Kumar Tyagi. I am PhD student at IIT Delhi. I work in intersection of medical images and computer vision. I'll be taking today's session for deep learning for computer vision, week 12, and we will be discussing self-supervised learning-based methods, mainly simCLR, some pretext tasks, and some clip-based embeddings, and how do we actually make use of them, right? So, like, I think we should get started. So the flow for today's session will be that we will look into few of the questions. I'll cross-refer few of the sections to the original papers where and how they were introduced, and we will actually build the topic on top of papers only, and then we augment everything with additional open source code base which is publicly available, right? And I'll just tell you how maybe few practical tips to make best use of these things, right? So let's start with self-supervised learning. I hope you understand what is self-supervised learning, where you are making use of data to learn good representations out of it, learn different clustering, different distances between the images. Suppose there are there is an image of dog, there is an image of different breeds of dogs, and so you expect them to be in some space. These two embeddings should be close to each other, as compared to, suppose this is a cat image, right? This is dog breed 1, dog breed 2, right? As compared to cat, these the similarity between the dogs should be more as compared to what is supposed to be between a dog and a cat, right? So we are actually making use of structures which are inherent in the images, right? And learning, in order to do so, we learn representation for each image or data point. So there was the the traditional form of doing this was this some sort of a k-means kind of architecture, where you have different data points, right? And you assign different points to clusters, right? And you try to minimize the distance between the centroid and the outermost region of this cluster, right? And there is something called the elbow curve, where you through which you identify that how many clusters are actually there in the your data, right? So this is the clustering based algorithms are also unsupervised, right? But you cannot actually use the learned representation into some downstream task. So self-supervision is slightly different from that, although it comes under the same subtopic, right? So you are not using any additional labels for self-supervised learning. You are using whatever the information you have in terms of your data only, right? You are making best use of that without touching any label part, right? So this contrastive learning is one of the things which actually helped grow this field, right? So let's get started with a few of the questions, and then we'll discuss more about it. In context of self-supervised learning, contrastive learning is widely used for representation learning. Which of the following statement is not true regarding contrastive learning? Yes, sir. Yeah. So contrastive learning aims to maximize agreement between differently augmented views of the same data sample, while minimizing the agreement between views of different samples. So this is true, right? the true form of contrastive learning is basically you're kind of identifying the similarity between these two data samples. Suppose you, you pass it through some encoder. So generally, when you're actually dealing with vision centric tasks, these encoders are called as the vision encoder, right? So it actually gives you embedding representation. So this is image 1, this is image 2, this is E1, this is E2, right? And what you do, you actually compute the contrastive loss between them, and uh, it is essentially like similarity computation between them, right? So you can actually use cosine similarity between them, right? Or maybe even the dot product, you can actually use some sort of exponential t, like e of e1 or maybe e2, some sort of this, or maybe a dot product, directly dot product between transpose, right? So different ways are there to compute the similarity, but essence is like you compute the similarity between the embedding, and the similar the embeddings are, better it is for us. So what we actually do in the contrast this self-supervised setting, we have I1 and we have a augmented version of this same image, right? So what is a I1 dash, right? So suppose this was upright image, right? And so the augmented version is maybe 90-degree flip, or maybe a down, like 180-degree flip along vertical flip. So this augmentation is right what we are trying to minimize. So, and the thought is basically that the context between the image is should remain same, right? So you should not be bothered about the orientation of object. You should be bothered about the localization and the attributes of the object. Suppose there's a dog which is uh, which is present in this image, right? If I am like if I just flip the image along the horizontal axis, now the head is around looking towards left. Earlier it was looking toward right, right? So this flipping should not change the attributes. Do not change the attribute of the dog, right? So why should we actually bothered about in what orientation or what color the dog is? Like, we should be focused on what is the object of interest in the image, and the representation for both of them should be same, right? Ideally both of them should be representing very similar. Maybe in one of the embedding they which might be about the rotation or the orientation of dog, which it might say that like it is toward left, or this in this embedding one like place can actually say that it is toward right. Apart from that, all the embeddings should be same because it has the same ears and everything should be same, right? So the contrastive learning ensure that like this similarities are similar representations are actually closer, and while doing so it automatically ensure that like there is some form of structure which is forming around it. So this is actually correct. In contrastive learning, negative pairs are typically formed by using artificially generated images, noise samples, rather than the real data point to improve the robustness of outliers. Uh, so, so using artificially generated noise sample, people actually use them, but like this is actually a wrong statement. But to some extent, people actually use these kind of representations as well. So suppose you have a data limitation in some way, right? Like you don't have like a diversity in term of colors, right? So You can actually do like color grading or color change as well, but that actually change the color grading of the whole image. So people have started using these diffusion models to help in the augmentation task. So what people generally do is they suppose we have maybe dog data set, and there is one breed which is very the color of that breed is actually very rare. Color of that breed is actually very rare. So what people have started is like using text information. They say that dog maybe pink, right, color, right. So this uh, so is supposed to actually generate a dog with maybe which has a color pink, right? And in your data set, you might have not have seen such images, right? But what people are doing is like they are also providing some skeleton or some reference image of the dog. So suppose I'm providing maybe Labrador, right? So I'll just say that like it should look actually like Labrador. It should look like Labrador, but the color is suppose I say that the color is pink, right? So people have started generating new data set using this uh, like which can actually act as the negative sample, positive samples, right? But not the negative sample. Negative samples you can actually crawl the whole internet, and you can simply say that like whatever is not the same image is actually a negative sample to you. But this is a very interesting paradigm which is being developed recently. So people are actually using for medical images as well. So there is something called the control net. I think we have discussed it in previous sessions as well. So in control net, what you can do is like along with your text information, you can actually provide some sort of a skeleton or some mask as well. So suppose this is the boundary of the dog which I have provided, right? And maybe a reference image as well. So this is a reference image, and your diffusion model actually generate uh, following this reference image, but the properties can be altered using the text information we have. So using this kind of paradigm, you can actually generate more samples. Like in case you have limited diversity, right? So you can actually do this. Maybe even the repose changes you can actually do. So suppose in your data set you have all the images where a dog is actually looking to either toward left and right, but not towards you, toward the camera, right? So like what you can do is like just in text you say that like the dog is looking toward camera, and then it will automatically generate images in a way that like it is the same dog but actually looking toward the camera. So this actually create diversity, and people are actually exploring it. So like something interesting and something to be mindful of. But this statement is wrong, right? Like so negative pairs are typically found by using artificially generated noise samples rather than the like real data. So anything which is actually not your original, like your selected image, can be used as a negative sample. You don't need to generate negative images from the noise samples. One challenge in contrastive learning is requirement of large batch size and the memory ensure the sufficient number of negative samples without which the learned representation may collapse. So this is true. So in the original paper as well, they have identified that the larger the batch size, better it is to learn the representation. So if you actually see that like at the end, what are we going to learn is that like you will have some hierarchical form of a clustering. So this is suppose this is whole is a cluster of dogs, right? Suppose you are images and lot of dogs. So in the in within the dog also there will be multiple clusters which can ensure that like there is a difference in the characteristics of the dog. So within a category there can be multiple subcategories which has slightly different characteristics. So suppose your German Shepherd is actually different from your Labrador, so and which is actually different from like your smaller dog like Pug and other dogs, right? So even within a category there can be multiple subcategories, right? And once you actually show uh, for a batch you actually show that like for a positive pair there can be lot of different categories. This ensure that like you are kind of minimizing uh, in this plane rather than like in a larger plane, right? So you ensure that like you are focused on that particular category rather than the multiple categories. So you are minimizing at the breed level, not at the dog level. So that actually helps. So this batch size actually help in that uh, paradigm. So they have shown through experiments as well that having a bigger batch size is actually helpful. Contrastive learning require labeled data to generate positive and the negative pair, as labeled data help differentiate between class, ensure that proper supervision between. So this is not right, not required. Like so, if when you are actually talking about the self-supervised learning, so there is no like connection to the label data. So uh, what they actually do for any image, augmented version of that image is basically what we are trying to minimize, right? So this is the category. So we actually don't take care of or use label in any format, right? So there is another version of self-supervised learning which is called the supervised supervised contrastive. So there is something called as supervised contrastive learning, where when you pick a positive pair, you ensure that like your suppose uh, let us change example. So suppose this is cat. We are from cat. We are picking the positive pair. So we know that like we have the label information as well at this point of time. So when you are actually ensuring when you are creating negative samples, in that case you will not use the examples of the cat as the negative pair. So you will use all the other categories, maybe dog, elephant, giraffe, whatever it is. But you will not use the dog as in dog samples in the sorry cat samples in the negative pair. So this supervision is actually coming from the labels in label information. So this variant is actually called as the supervised contrastive learning. So if you have labeled information, right, and actually you want to learn a representation of objects, so this is actually very useful. Let me just show you paper as well. Let me show you a paper of this. So there is one question: why AI models still struggle with generating left-hand related images even if we use self-supervised learning. I did not. I mean, I just gave an example. Like, it's not that like left hand related. Okay, right? So, I mean, there is a bias, right? So, uh, like, if you actually say that, if you actually say that, like, images of chef or images of generate images of doctor, uh, like there is a high chances, or like maybe in the like say that like generate images of a construction worker. So there are high chances that the model will be generating images of men who are working in the construction sites. So because there is a bias that like only men are actually working in these construction areas, right? Although it is not true, right? Women are also being representative, but there is a when we are actually collecting data, so a lot of data we are collecting is basically biased toward men, right? That's why your models actually inherit that bias, and when you are actually generating these images, suppose writing from left hand to right hand, right? So people, this model actually struggle in those low data regime cases, right? So that is the bias of the society, or like kind of the data we are feeding into the system. So there is a field where like people are trying to see that in what cases these models are biased, and how do we actually make these generation more fair. So that is also an interesting aspect of these generative models. But the bias, if you even if you actually look into the earlier model of these GPT-2 or GPT-3 as well, the earlier version, not GPT 3.5, so they also inherit a lot of bias, right? So after uh, this OpenAI identified that there was some sort of a bias, right? They actually did a like refinement or the alignment task, where they try to make model much more fairer. So yeah, that is the case. So yeah, it's in the like society, and maybe the quality of the images we are actually collecting. I hope I answered the question. This is what it meant. Okay. So let me just show you the paper of this. So this actually came in 2020. This is actually very famous paper of a simple framework for learning, contrastive learning for visual representation. And if you are actually working in like in AI, you should actually know that this person is Jeffrey Hinton, and he is called as the godfather of AI. He is one of the three people who was awarded Nobel Prize, I think last year, I guess. Yeah, so other one, Yoshi Benjoa and Ian LeCun. So he has done very fundamental work from backpropagation, optimization, and training DNNs and all those stuff. So yeah. So this is actually the loss function of your uh, simCLR, and it's basically the contrast loss. So you are doing some sort of a similarity matching between Z1 and ZJ. So this is and this, there is some temperature factor tau is there. The tau ensure that like how sharp or how spread out you want it to be, right? So this temperature factor is also uh, there in what do you say, if in your generative models, like even ChatGPT or the earlier models as well, if we actually access the API, not the like web interface. If you actually access the API, you can actually try and play with this temperature factor. So one end actually ensure that very steep like graph, which ensures that there is no stochasticity there, low, and the other hand actually ensure that there is a much more uh, uniform kind of a distribution where there's a slightly possibility of the stochasticity. So if you want your model to always give the same answer, then you what you say you make it, I guess, uh, temperature, I guess, 0, or the other way around is like you have there is some scope of stochasticity, then you actually make it I think it is other way around, but yeah, anyway, so the range actually defines how how much stochasticity you want it to model. In the denominator you have all the negative samples, so you have all the negative samples except the one you are actually selecting for the positive pair. So this is your contrastive loss, right? And the algorithm is actually very simple. You compute the pair, you do the augmentation, you compute the pairwise similarity between them, and everything which is not that pair is basically the negative pair, and you ensure that you have some peak uh, with respect to your all the negative samples. Your distance should be minimum, and you do different type of augmentation as well. So you do crop, resize and flip, color distortion. You make RGB to gray. You distort the channel, right? So you make only one channel. So in this case, they have actually made it only green channel. Rotation, cutout is basically you cut a portion of the image, and you still expect the based on the other attributes, the embedding should be able to identify that this is the same object. Then you add some noise, some Gaussian noise, different blurring, even the Sobel filtering, where you actually give the boundary or the edges of the object, right? So based on the outer structure only, your model should be able to identify that this uh, both of them are actually similar, right? So what I wanted to show you is, yeah, so this is what I wanted to show you. So if you actually see, that, right? So this is 256 batch size, and you can see that for if we actually train for 100 epoch with 256 batch size, your accuracy is close to 57.5, whereas you train it with batch size of 8192, right? Which is then your accuracy is close to 65.0. So batch size actually matters, but if we actually train it for a longer epochs, there is the gap between the lower end and the upper end of the batch size is actually reduces. So that actually makes sense, right? So when you are actually training it for longer epoch, you are telling all the possible negative possibilities which can have for a positive pair. You are in a way showing it to the model, right? So like if you have good amount of compute, uh, you try with higher batch size, you don't need to train for the longer epochs. If the compute is limited, then you might need to train it for a longer epochs, so that you can compensate for this batch size constraint. Makes sense, right? And how do you actually evaluate is something which is interesting. So So for this image you are getting Z at the embedding, right, and you are ensuring that like your augmented version of the image is also generating the embedding which has the maximum agreement or the maximum similarity between Z and ZJ, right. So when at the test time you will get is you will get this Z embedding, and now what you can do is you can using this embedding you can train a single layer classifier. uh, so this is encoder and head. uh, So there is something called as a linear evaluation. So what you do is like you have a linear classifier on top of this embedding. So something called as maybe logistic regression, right? So you train a logistic regression on top of this embedding and just report that accuracy. So this is one way of evaluating your embeddings, right? So if your embeddings has already defined your data into different clusters, that so the embeddings for different cluster will be slightly different, and your logistic regressor will be able to identify the decision boundary for that. So this is one way. So another way is basically you on top of your embedding you learn a nonlinear representation where you add one layer of suppose DNN and use that to classify. So right, and you do it for all the methods. So if these are the different methods, like I'm comparing with, I'm also do the same thing with other methods as well. So whatever the representation I'm getting, suppose it's a 256 dimensional embedding, or maybe right, whatever the dimension output dimension is, right. So on top of that I'll just do a non-linear projection to some, say suppose 10 cross 10 cross 1, right. So and on top and use this learned representation, like the projected representation to classify whatever the categories or whatever the downstream task I'm using it, right. So then you actually do this top 1 and top 5 kind of a classification where you say that right. So if I'm saying like I rank my prediction, and if my top first prediction matches with the correct, then I'm good to go, right. And then top 5 is basically my prediction should be at least in top 5. So that's why you say that like your top 1 is suppose 69.3, then in top 5 it is 89.0. So this top 5 actually gives some sort of a buffer that at least it's not first, it has to be in at least in top 5. So this kind of buffer is sorry, I think I was not sharing the tab, but yeah. So this is what I was actually saying. This graph. Sorry, I didn't share the tab. So I thought. Yeah. So this is what I was saying. If you can see that like from the lower end to the upper end, the batch size is differs from 256 to 8192, right? And the gap is actually close to maybe 8 points, right? If we actually keep on increasing or the training number of epochs, you can see that the gap is actually reduced. So like if you have, so this is the trade-off, right? So if you have good amount of GPUs, you try to increase the batch size. You need to train only for the lesser number of epochs. If you have, if you don't have a good amount of GPU, you might need to train for a longer period of time. And what I was discussing, this linear classifier, where you use the whatever the embedding your model is giving, learned model is giving, you just pass it through either a logistic regressor or a single layer of DNN and do the evaluation of top 1 and top 5. And the good thing about this is, like you can see, right, like the backbone architecture is resonant 50, resonant 51, 61, like these variants, right? So you can actually transfer this knowledge to different downstream tasks as well. So this actually gives a very good starter point, right? So if you are actually using it for maybe image segmentation or even object detection, you can use this pre-trained model, right, and do the object detection. So instead of basically starting from scratch, so that actually gives a good amount of boost and a better convergence, or the like quicker convergence in most of the cases. What would be the need for evaluating logistic classifier? So, so what we are trying to do here is we want to see how good the learned representation are. So you have trained the model using simCLR or contrastive loss, right? And your model has actually learned the representation. So how do you actually evaluate that? So what you do is, like, you take for an image, you take the embeddings, and what you do is, like, using for this embedding, you either uh, train a single layer neural network to do the prediction, or maybe directly use the logistic regressor to identify the decision boundaries for this data set. So you pass on whole data set through your like learned model, get the embeddings, do a logistic classification on top of that. So now you get a sense that without any additional uh, information, you are able to still able to cluster this information of your learned embedding, right? So that actually shows how good uh, the model has actually understood the data. So this is basically the evaluation metric, or the way of evaluating the representations. Right, so because it's completely supervised, like self-supervised, right? You don't have any information. We have not shown any type of label information, right? So uh, yeah, so that actually shows that, like, model has learned that these categories are closer, these categories are far from this category, and logistic regressor can actually identify a good decision boundary between multiple categories, so that that actually makes the task of your logistic regressor or any classifier easier, right? So that, like, will tell that, like, that ensure that a model has actually learned the good representations. Is it clear? Any doubt till this point? I just want to quickly tell touch upon this as well. So whatever we saw was self-supervised. So there is another variant of it, which is the fully supervised setting, where uh, where you ensure that the positive class and negative class need not, like, suppose in this case this is a self-supervised setting where you have dog, this is the anchor and this is the positive class, right? And where the other dog can be present in the negative class as well. But like uh, whenever in this supervised setting, you ensure that, like, suppose you want to pick for dog, you pick um, another dog, like, because you know the categories as the positive class, right? And your dog category will not be present in the negative class. So it actually makes the clustering or the learned representation, the gap between the learned representation much more better, right? Uh, so, so this dog coming here can create some sort of a noise in the system, although uh, as compared to whatever the negative classes we have, the proportion will be very small, but it will still be a noise. So what in supervised contrastive learning, you ensure that the dog is not in the negative category. So but then the formula actually remains same. Only thing, we ensure that how you are actually identifying this, what you say, the positive and the negative class. This is uh, this is useful as well, right? So um, in cases where you have the ground truth information, but you want to learn a representation of the object, right? So that in that space actually it becomes useful. So in one of our work as well, we wanted to have a learned representation of cells. So, and these cells are actually very small. So we were actually distinguishing them based on different attributes like size, shape, intensity, right? So we use the supervised contrastive laws to learn the representation for cell, and if you actually, when we visualize the cells, you can actually see that different categories, different type of cell has different clusters. So the learned representations were actually non-overlapping to some extent, and had already captured this different attributes of these images. So that is actually very interesting. So coming back to where we are. So next is actually the pretext task. So pretext task was also like the idea which was like very prominent, um, and like both self-supervised learning and the pretext task were actually some sort of parallel ideas which were very popular earlier. So what does the pretext task mean? I mean, it's like you are actually learning from the data. Only thing is like you are learning while solving some sort of a different uh, task or like small puzzles, right? So suppose this is my image, and I, what I do is I rotate it 90 degrees. Maybe the orientation is toward this, right? Earlier it was this. So what I was doing is like, can I train my model to such a way that like it should be able to predict that what is the rotation of this image, right? Suppose it says it is 90-degree rotated, then it has learned that representation that like there was some object which should be upright, but it is actually rotated 90 degrees. So suppose there was a tree here, right? Now the tree is actually in this, right? Yeah, toward moving, looking toward left, right? So now what we have done is like the model should be able to predict that it is a 90-degree rotated image, right? So there was this was the rotation. The other one was like the jigsaw, where you shuffle the tiles, and suppose this is 1, 2, 3, 4, 5, 6, 7, 8, 9, and you shuffle them, right? So now this becomes maybe 4, 7, 8, 9, 1, 3, 2, 6, 5, right? You shuffled them, and the objective of the model was to actually predict what should be the order of this, uh, like deshuffled, what should be the deshuffled order. So like where this, so it will predict something like 1, 2, 3, 4, 5, 6, something like that. So at first, this should actually be here at the first place, right? 2 should be at the second place. So this this should be the order of the prediction. So in order to do so, it learn the representation that what is present in the image and what how even so it actually looks on what do you say, the whole structure of the object, and like in order to do so it focused on the local part, right, not on the like maybe the global part. So it identify some ears are basically on top of your eyes, so that correlation it actually learned. So that actually become very useful like when we are actually doing some sort of a pre-training as well, right? So let's look at the question, what question is asking. uh, Several pretext tasks in supervised learning use specific augmentation like jigsaw puzzles, rotation prediction, colorization. These tasks help the model learn useful representation without label data. Which of the following statement about the pretext task and augmentation is not true? Right. So first one is jigsaw puzzle involve dividing the image into patches and shuffling them. The model predicts is trained to predict the correct arrangement of patches, encouraging spatial reasoning in the visual representation. So this is actually true, right? So that's what we are trying to do here. The rotation prediction as an augmentation teaches the model to recognize object orientation by rotating the image randomly to different variant and training model to predict rotation angle, which leads to learning rotation invariant features. So this is also true, right? The pretext tasks like jigsaw and rotation are designed to improve performance of image classifier, uh, the but are generally ineffective in transferring to tasks like object detection and semantic segmentation. So this is wrong. Why? Because whatever the learned representation we are learning, we are training some sort of a backbone. So this is ResNet, right? Suppose, and this ResNet pre-trained model, we can actually use it for different tasks like object detection or semantic segmentation as well, right? So this backbone is you can actually translate to different tasks, and on top of that you can actually learn maybe in case of segmentation you learn some sort of upsampling you learn some sort of upsampling or deconvolution method where your objective is to basically predict segmentation mask. In object detection you might want to actually predict like some localization of the objects, right? Jigsaw task is considered to be invariant to local structures distortion, making it effective in preserving the fine-grained detail of the images even when the patches are shuffled and reassembled. So uh, this is not true, right? Like so local structure, if you are actually splitting the image into local patches, you are uh, like distorting your global structure, but uh, so it doesn't actually make it invariant. So it start focusing more on these local structure to identify how from local it can actually go and understand the global structure of the whole image. So this is actually wrong. So if you actually want to see the paper, I will share. This is the this is the paper, and it is unsupervised learning of visual representation by solving jigsaw puzzles, and this is what they did. So for an image, they shuffled the whole divide the image into patches, non-overlapping patches, shuffle them. The objective is to retrieve back the whole original image, right? And this is the architecture you have so So what they do is like you define different permutations for patch. So suppose this is the permutation of 946832517, and you assign a value to it, right? And your model should be predicting that this is that permutation. So it is basically predicting that index of the permutation. So 64 it is predicting. So it learns that, like, in order to go back to the original image, what changes I need to do. So let me just put it in the chat. So next, moving to next question, in simCLR, so this was the paper which we have seen earlier. So this was self-supervised contrastive learning paper. The choice of data augmentation is critical for learning robust representation. Which of the following statement about simCLR's augmentation strategy and its role in contrastive learning is true? simCLR primarily use augmentation such as random cropping, horizontal flip, color distortion to create diverse views, uh, which help in learning invariant features. This is true. Use of stronger augmentation such as heavily blurring and noise injection in simCLR is beneficial for all time string tasks, as it increases the variety of training sample, ensuring uh, robust representation. So this is actually not true, right? Because if you are actually using very heavy augmentation, so these are called as the hard negatives. So to some extent it is fine, right? But if you are almost distorting the whole image, then the model start to learn uh, random features, right? Maybe it start to focus on background, right? And maybe some local attributes. Then the whole purpose of doing the contrastive learning actually becomes irrelevant. So you do some sort of so there has to be some sort of a balance between like soft labels and the hard so, soft negatives and the hard negatives. So hard negatives should be those cases where you are actually uh, like hard negatives actually make your model more robust, but not all or like hard augmentation. If you are actually injecting too much noise into the what you say your images, then it actually become your model. It becomes difficult for a model to actually say that like both of them are actually similar. So that is not advisable. Combination of augmentation is designed to ensure that the view maintains enough semantic content to provide positive pairs while we still be differently uh, while still being sufficiently different to avoid trivial solution. So this is true, right? Like, so this is what we are discussing. So there is a like range of maybe some soft negative between hard negative. So what is a hard negative? I think if I can come up with an example. So suppose like if you actually look at your maybe the distribution, right? Maybe different categories are there, and so this is your, you sample an image from this point, right? So this is your image one. Images which are with here, right, data points which are close to boundary, these are actually the hard negatives. Suppose you're doing a cat, just a minute. So I'll come to this option B actually. So the hard negatives are which are very actually close to boundary, right? So suppose you have a cat and you identify that there are some dog which is basically very similar to that cat. So if you are actually including that dog in your batch, then you are ensuring that like there is a hard negative which is present in the batch, and your model will be forced to focus more on the cat features, where you like you, so that like you are able to identify that there is a decision boundary around this hard negative, right? In term of adding noise, right? So what noise can actually do here is they can actually push these into this category, right? Too much noise you can actually push the samples which are actually at the boundary to the other category. So uh, then if you're pushing them into this category, then actually it becomes very difficult for your model to identify the meaning, right? um, Suppose, yeah, so suppose there's a dog which is an black, which is a black dog, right? So, and there's a buffalo which also have the same color. So if you keep the buffalo in as a negative sample, then model actually learn that there is a size variation as well. So dogs are actually very smaller as compared to the buffaloes. So the color is not the only trait where the model should be focused on, right? So in the same example, if you are actually blur the whole image and maybe shrink the whole object, then uh, like the buffalo also can look like suppose a dog, right? So you don't want that kind of noise to basically perturb your whole image samples. So a limited amount of hard negatives are good, but adding too much noise that actually make your model like the whole data samples corrupt, that you don't want to. So heavily blurring uh, is not advisable. So noise injection is fine. So you actually do Gaussian blurring, you add Gaussian noise, that is actually fine, but you ensure that while doing the whole thing, you ensure that the property of the object still remains intact. So that you don't actually change the representation of the object. So yeah, that's why B is actually incorrect. So you don't want. So denoising autoencoder is fine, yes. Yeah, so denoising autoencoder also has some certain limit, right? So even the mask autoencoder also comes in the same category. So suppose there is an image, you remove maybe some 10 or maybe 25 to 30 portion of this image, and your model, your autoencoder still will able to reconstruct the whole image, right? So this is fine. So but suppose you are actually making, you're masking out 90%, 80 to 90% of the region, then your model is actually predicting something rubbish. So, so adding noise is fine, but to some extent. I hope it is clear. simCLR uses augmentation like random cropping, color jittering to artificially inflate the size of the dataset. So this is actually wrong, right? So this is not what you are doing. So random cropping and everything is just to create a like different version of the same data sample, so that like we're able to maximize the similarity between these two versions. Right. So in simCLR model, a batch size contains 512 images, and each image generates two augmented views. Assuming each augmented view has exactly one positive pair, calculate the total number of positive and the negative pair in the batches. So, like you wanna like try how does it, how many positive pairs will be. So there are, suppose n is 512, right? Um, and for each sample you will create a positive pair. So you will have 2n, so you have 2n of positive pairs, right? And how many negative pair will be? So you will have uh, so 2n minus 2, right? So basically whatever the positive pair we choose, I will need to actually remove it from your negative pair. So we are not using that as a like positive pair. So everything apart from that pair is, or everything is negative. So you have maybe 1 0. So what is the question is, calculate the total number of positive pair and negative pair in a batch, right? So for negative pair, for each positive pair, so you agree, right? Like there will be 512 positive pair with uh, 1024 as the augmented views, like 1024 views, right? For each positive pair you'll have this amount of negative pair. So in a batch, suppose a batch can take whole data set. So that means like you'll have this amount of negative pair for each of this. So that means that like you'll have in the whole batch, and this is amount of forward. This is positive samples actually, like, so pair is actually one for this, right? This is amount of positive pair. For every positive sample, you'll have all the other sample as the negative pair. So this is basically we're talking about. I hope previous was clear. If you have any doubt, just put it in the chat. So this is contrastive language image pre-training. So similar to what we have seen till now, we have seen that like whatever the contrast wave retraining we were doing was basically between images. So similarly, they extended the concept to image and what you say, image and text. So what they do is like you have image encoder, you have text encoder. So this has image, it has some text, and it generates some sort of embedding, right? And for each word, you do some sort of a similarity matching based on some sort of similarity matching. So this can be high, this can be high, sorry, this can be high. So and suppose dog, and there is the image of dog which is present in the image, right? So this uh, will have some sort of a similarity. This also will have some sort of a similarity, but dog will have a very high similarity in term of your image. So, and you are trying to minimize, you are maximizing the what you say, maximize the similarity between the image and the text embedding. So you ensure that both of them actually capture the same thing. So this embedding actually captures the representation for context dog. The image embedding also captures the context of dog, right? And you actually do the similarity matching between them, and right. So at what do they do at the test time? So you have the image of suppose dog, sorry, right? And and at test time you'll say that okay, you don't know, right, like what this image corresponds to. Suppose this is empty, right? And you you have the information about what are the different categories are present. Suppose there are 5 categories are present: dog, cat, other, right? And you do some sort of a similarity that if I place dog here, what what is the score, similarity score I'm getting? What if I place cat here, what is the similarity score I'm getting? What if I place elephant, what is the similarity? And you pick the highest similarity score and assign that word to this blank. And this pre-trained embedding is actually very useful, right? In one of our Kaggle competition, we were actually trying some sort of multimodal thing, and like we tried everything like GPT 2 and or like you have VIT, and we were using chat GPT to extract out text embeddings, and we were trying to fuse the information and then doing some prediction, but nothing like was working. Uh, the, then we actually tried this clip embedding where you are actually feeding text into this text encoder, and your images was fed into the image encoder, and then whatever the resultant embedding came, we trained a very simple CRF, some random forest based XGBoost, I guess, on top of this embedding, and it beat all the very complicated like architectures people were trying. So I mean, these embeddings are actually trained on vast data, and like if you are actually doing something related to multimodal, like the suggestion is always start with pre-trained architectures. If you let me just share Hugging Face. So if you can open this document, so this actually has lot of information about clip embedding and other type of embedding. So and this is actually a very good starter, so you don't have to do lot of code, only just load the pre-trained weights, pass on the text information or the image information, and you will get uh, the relevant embedding. So this is actually very useful. So I mean, my advice would be to, whenever you're starting with some sort of a multimodal thing, just try or start with this clip embedding. Okay. So contrastive actually, let me just show you the paper since we are here. So this is the paper for clip embedding. Learning transferable visual model for natural image supervision. So this is what they are doing. So you have a text encoder, you have image encoder, you have embedding representation for text, and you have embedding representation for images, and you're trying to maximize this similarity between embedding 1, text 1, embedding 2, text 2, embedding 3, text 3, right? And at test time you have image representation, you have multiple text corresponding to this, and you only pick the text which is basically maximizing your similarity for with respect to image. So and it outputs this is the photo of a dog. So like this dog can be a place, car, dog, bird, whatever the possible categories are there in the data set, right? And you pick the one which actually has the maximum similarity with respect to your image embedding. Yeah, on top of logistic regression, on this clip score they actually do similarly. On the clip embedding they just train a logistic regression and do some sort of a classification, and they say that like using this clip embedding for most of the data sets you see that there is a increment maybe of this amount of points. Okay, so going back to questions. So clip embedding has demonstrated strong zero-shot performance. What is zero shot? So like if I am not trained at on some other uh, images or data, I'll just say that like although this model was not trained on these images or this data, I'll still use that to give me some prediction. So that is zero shot prediction. So model has not seen that data. On variety of tasks while learning joint representation of image and task, which of the following about clip architecture, training strategy, and generalization ability are true, right? So clips contrastive learning objective uses dot product of image and embedding to compute the similarity, which are then normalized by the softmax function to align positive text pair. There is one. actually true, although although the answer is written as false, but actually it is true if you actually look into the paper. I think this is true. You can check. Uh, Clip use two separate encoder, one for images, one for text, allowing both modalities to project into the same latent space where cosine similarity used to match the corresponding pair or contrast. So this similarity can be, I think, dot product as well. So, but it has two separate encoder and the decoder, not decoder. So image encoder and the text encoder. So this is true. One of the main reasons for clip embedding to perform well on zero-shot tasks is due to its training on a wide variety of text-image pairs from diverse sources, enabling the model to learn general representation that is transferable across the task without fine-tuning. I think this is true. Clip's zero-shot capacities are primarily limited to object classification tasks, and the performance on more complex tasks such as image captioning, visual concept question answering requires additional fine-tuning. This is not true, which is basically similar to what we have seen in simCLR, where image model which is trained for object classification can be extended to object image segmentation and object detection. So this is not true. So only doubt we have is about this. Just check the paper. I think they use so the order is actually slightly different. Let me just show you what is the order is. So what they do is, like, you have embeddings for text embedding and image embedding. They do normalize it, then they compute dot product, and then they produce and then there is no softmax actually, softmax function to align them. So they simply right, so they simply do the dot product and then just do the normalization. Sorry, normalization and dot product. So this is what the routine is, but I don't think there is a softmax here. So we are talking about this. Uh, so this is actually false, only because the order in which they are doing is like wrong. So but dot, they actually do compute the dot product between the text and the image embedding. So answer is so blip is one of another variant, and there are two versions of blip. So blip 1 and blip 2 are there. So So, blip and blip 2 models are advanced multimodal vision language model for combining vision and language. Pre-training which of the following statement about blip and blip 2 are true. Blip uses vision transform, vision language, contrastive learning objective to align image and text representation and shared latent space similar to clip, but it also incorporates the captioning objective for uh, better language generation. That is, so this one is actually true. Blip 2 introduces two-stage training, where the first stage using frozen image encoder and second stage fine-tune both image and language encoder to reduce the computation and data efficiency. This is also true. Both blip and blip 2 model rely heavily on manually annotated uh, large scale image text data set for pre-training. So this is actually not true, right? So they crawled the internet and identified image and text pair corresponding to that. So there is no supervision there. Blip 2 built on Blip architecture by incorporating the Q-former, which enables better fusion of image and text for both generative and the discriminative task. Right. So what is a generative task? So generative task is when you're actually based on image caption generation. So suppose you have an image and you want to generate the caption corresponding to that image. So that actually corresponds to a generative task. What is the discriminative task? So suppose you have an image and you want to identify what is the category of the object, or maybe do some sort of a classification on top of that image. So that is actually a discriminative task. So that's how this discriminative and the generative task actually works. So this is what let me this is what we have for questions. Let me share a few repo for simCLR. So I hope you can see this. So this is the like official repo for simCLR. So and it is actually built on PyTorch. And what you can actually do here is you can open this. So they have like given what do you say, different architectures, and they have different performance as well. So this is the projection head of this ResNet 18, right? So and your feature dimension is what we were actually like think. So Z is actually this feature dimension. So and you have from this feature dimension you project it into a unified space which is 128, so that all the operations or can be done in the same space. So that like there is no disparity between the dimension of the final embedding dimension. So on this 128 dimensional vector we do some logistic regression to identify whether we are able to identify the patterns or not. So they report top 1 accuracy as well. So this is one thing. So this is the notebook actually which I was using when I tried learning this simCLR. So yeah, so you do the normalization, you compute the similarity between them, and you do whatever the contrasted learning loss was there, right? And how the good thing was, we actually trained it, and you have a logistic regression, you get the embeddings, and you on top of the embeddings you actually train this logistic regressor, so you get close to like 75% accuracy. And I actually trained it for not much epoch, right? I just simply trained it for few epochs, and so that like only based on these embeddings you are able to get a good amount of classification kind of thing. Then people actually try using only 10% of the features, right? So just take 10% of your data set and now train the logistic regressor, and if you are still able to identify, you do good on your test set, then that means that you have learned good decision boundary. So you can see that, right? Like In on the test side with only 10% of the images, I am able to get 73.75, and the whole complete was like 75. So if in this case also the model is able to learn good representations. Uh, so So the rule of thumb is actually that, like, if you don't have your suppose in most of the cases, like suppose you are working on medical images, not medical images, so natural images. So in those cases you already have good amount of pre-trained models. So you have large data, you have models which are basically pre-trained on ResNet, VIT. These things you can use as the backbone. Suppose in the domains where you don't have sufficient label data, what you can actually do is you can use the self-supervised learning based architectures to pre-train a ResNet like architecture on your data. So suppose I work on medical images or maybe histopathology images, or someone might be working on the satellite images or some other domain where the data is very limited. You have what you say, images are there but label data is very limited, right? So in that scenario what you can do is you can use this contrastive learning or like self-supervised learning based approaches to pre-train your model, uh, and then use this pre-trained model for your downstream task with limited labels you have. And using this approach you will see that like there is a boost in whatever the performance you were getting earlier, right? So do not expect that there will be major boost, but definitely this actually improve your learning, and like the amount of time requires to learn, the convergence is actually better. So uh, this is another way of handling things when you have limited data. So yeah, this is all I have. Let me think if there's something I'm missing. I have put a repo of simCLR in the chat, so if you want you can actually try and run it. So now, like this, all these models, right? Maybe ChatGPT or whatever the like the latest models are coming up. So they are also trained on the similar kind of tasks. So they are so there are different tasks were defined for designed for this natural language models. Like so these LLMs. So one of the tasks was like, suppose I give you sentence one, can you actually predict the sentence 2, the next sentence prediction, or maybe fill in the blank like task. So if I give you sentence, what I'll do is just mask out one of the words from the sentence, and here the objective will be to, based on the context, can you identify what is the that word is, right? So fill in the blank matching the sentences. So suppose like you give the sentence and then you have multiple options. What like you have sentence one, you have multiple options. Sentence two can be this A option, B option, C, D, right? And then you just connect with the what is the correct option. So uh, right, so even the latest models, these are also trained in this self supervised manner. So this is actually like very useful because you don't need a lot of data, right? So even for fill in the blank, right? So I can actually simply crawl the whole internet and use just like tokenize the sentences and just uh, mask out one word from the sentence and tell my model to basically predict what is the missing word in the sentence. So in that way, I have created lot of billions of such examples. and this actually gives a very good understanding of the context, the language, what word, and the grammar also, right? Like, so you not only predict the word, you also predict the correct form of that verb. So, like all the hierarchies of this language are being learned using these self-supervised learning-based methods, and even in the image space also. But in image, it is slightly limited because the amount of images are way less as compared to what the text is present in the world. So you have Twitter data, you have Reddit, you have Stack Overflow, all the data they have crawled and used it to train. So when we actually do the same thing for images at the same scale, you will see that your the images will also have the same kind of capacity as compared to what these LLMs are. Even for the video generation, image generation, they are good, but not par with what the coding agents are at this point of time. So over the time, I think like people are actually working out on identify how can you improve this video generation or video understanding agents. Yeah. Any doubt or yeah, just let me know. We have some time. If there is no doubt, then I think we can close the session. Um, I think we have a class tomorrow as well at the same time. If you want, you can actually join. And if you have any doubt, you can actually we can keep that as the doubt session, doubt clearing session, right, tomorrow. Okay, then I'll just close the session. If you have any doubt, just put it. I'm not sure. I'll show you. If I already shared your email ID. Okay, anything else? Okay, then I'll close the session. Thanks everyone for joining. Good luck for your exams and whatever you do next.